Picture a machine filling packets of rice. Weigh them one at a time, and the numbers scatter, some light, some heavy, with a long tail off to one side. This population is lopsided. Nothing bell-shaped about it. Now do something different. Scoop up 50 packets at a time and write down just the average weight of each scoop. Then histogram those averages. Something almost magical happens. The averages pile up into a smooth, symmetric bell, a normal curve, even though the raw weights never did. That single fact is the central limit theorem, and it is why so much of statistics leans on the normal distribution. By the end of this lesson, you'll not only see why, you'll use it to build a confidence interval for a true average. Let's build this carefully. We take a sample of size n observations, each drawn the same way and not influencing the others. We call that independent and identically distributed. Every single one shares the same population, mean mu, and the same variance sigma squared. The star of the show is the sample mean x bar. Just add up all n observations and divide by n. It's a number you compute from your data. But here's the subtle part. Because the data is random, x bar is random too. It has its own distribution. First property, and it's a reassuring one. The expected value of x bar is exactly mu. On average, the sample mean lands right on the true population mean. It doesn't systematically run high or low. We say it's an unbiased estimate of mu. Second property, and this is the one that does real work. The variance of the sample mean is sigma squared over n. Take the square root and you get the standard deviation of x bar, sigma over root n. This quantity has a special name, the standard error of the mean. Notice sigma is fixed. That's the spread of the population. You can't change it. But n sits underneath a square root. So as your sample grows, the standard error shrinks. Slowly though. To cut it in half, you don't double n, you quadruple it, because root 4 is 2. Picture the distribution of x bar for growing n. Every one of these bells is centered on mu. That never moves. What changes is the width. A small sample gives a wide, uncertain bell. Grow the sample and the bell tightens around mu. The sample mean becomes a sharper and sharper estimate. That narrowing is the standard error at work. Here is the theorem itself, staged. On the left, our skewed population, the same lopsided shape as before. On the right, an empty axis where we'll collect the averages of many samples drawn from it. A handful of samples so far. The averages already avoid the extremes. More samples and a clear mound is forming, centered near the population mean. Push it to the limit. Thousands of samples, and the histogram of the sample means settles into a perfect bell, a normal curve, no matter how crooked the population on the left was. That is the central limit theorem. Written down. For large n, the sample mean is approximately normal, centered at mu, with variance sigma squared over n. And the plane sum of the observations is approximately normal too, with mean n times mu and variance n times sigma squared. Three conditions keep it honest. The observations are independent, the variance is finite, and n is large enough. A common rule of thumb is n at least 30, unless the population is wildly skewed, in which case you want more. Once x bar is approximately normal, we can standardize it. The same trick that turns any bell into the one reference bell. Subtract the center mu, then divide by the spread, which here is the standard error sigma over root n. The result, z, is a standard normal, mean 0, variance 1. From there we read off probabilities using capital Phi of z, the area to the left of z under the standard bell. One symmetry does a lot of the lifting. Phi of minus z equals 1 minus phi of z. We'll lean on that in a moment. Now the payoff of all this machinery, a confidence interval. We flip the logic around. Pick a confidence level C, say 95%, and find the Z, that captures that much probability in the middle of the standard bell. Substitute z equals x bar minus mu over the standard error. Then rearrange so that mu sits alone in the middle. Out falls a statement that mu lies between x bar minus z standard errors and x bar plus z standard errors with probability c. So a two-sided confidence interval for the true mean, when sigma is known, is simply x bar plus or minus z times the standard error, the sample mean at the center, and a margin on each side. Geometrically, z marks where the middle 95% of the bell sits. The shaded band between minus z and plus z is your confidence level. The tails left over are the 5% you're willing to miss. Three z values are worth memorizing. For 90% confidence, z is about 1.645. For 95, 1.96. For 99, 2.576. And read the trade-off in that list. Demand more confidence and z climbs, so the interval widens. More certainty costs you precision. Gather a larger sample instead, and the standard error shrinks, tightening the interval for free. Let's put it to work. A factory checks batches of 300 items. Each item, independently, is defective with probability 0.25. Let y be the total number of defectives in a batch. We want the probability that y lands between 60 and 90. Y is a sum of 300 independent yes-no variables, so the central limit theorem applies. First, its mean, n times p, 300 times 0.25 is 75. Its variance, for a sum of Bernoulli trials, is n times p times 1 minus p, 300 times 0.25 times 0.75, which is 56.25. Take the square root and the standard deviation is 7.5. So y is approximately normal with mean 75 and variance 56.25. Standardize both bounds. The lower bound 60 becomes 60 minus 75 over 7.5, which is minus 2. The upper bound 90 becomes plus 2. Now the probability that y sits between 60 and 90 is the probability that z sits between minus 2 and plus 2. That's phi of 2 minus phi of minus 2. Phi of 2 is 0.9772. By symmetry, phi of minus 2 is 1 minus that, 0.0228. Subtract, and the answer is 0.9544, about 95.4%. Exactly the Within-to standard deviations result, and now you've derived it. Second example, a confidence interval, start to finish. A factory makes metal rods whose population standard deviation is known to be 12 millimeters. A sample of 36 rods has an average length of 50 millimeters. Find a 95% confidence interval for the true mean length. Step 1. The standard error. Sigma over root n is 12 over root 36. Root 36 is 6. So that's 12 over 6, which is 2 millimeters. Step 2. The margin of error. 95% confidence means z is 1.96. Multiply by the standard error of 2, and the margin is 3.92 millimeters. Step 3. The interval itself. The sample mean, 50, plus or minus the margin. 50 minus 3.92 is 46.08. 50 plus 3.92 is 53.92. So our 95% confidence interval for the true mean rod length runs from 46.08 to 53.92 millimeters, roughly to standard errors on either side of the sample mean. Your turn. A sample of 64 measurements has an average of 250, drawn from a population with known standard deviation 20. Pause the video now and build the 95% confidence interval yourself. I'll wait. Here's the walkthrough. The standard error is 20 over root 64. Root 64 is 8, so that's 20 over 8, which is 2.5. The margin is z times the standard error, 1.96 times 2.5, which is 4.9. Then the interval is 250 plus or minus 4.9. So mu lies between 245.1 and 254.9. If your endpoints match those, you've genuinely got this cold. Well done. Trap 1. And the most common by far. Sigma is the spread of individual observations. Sigma over root n. The standard error is the spread of the sample mean. Forget to divide by root n and your interval comes out far too wide. Trap 2. The central limit theorem describes the distribution of the average, x bar or the sum. It says nothing about a single observation x, which can stay as skewed or as discrete as it likes. Trap 3. The interpretation. The true mu is a fixed, unknown constant. What's random is your sample, and therefore the interval. So the right reading is, if you repeated the sampling many times, about 95% of the intervals would contain mu. Not that this one interval has a 95% chance. Let's lock it in. The sample mean has standard deviation sigma over root n, the standard error, which shrinks as your sample grows. By the central limit theorem, that sample mean is approximately normal, centered at mu, for any population with finite variance once n is large enough, and with sigma known, a confidence interval for the true mean is x bar plus or minus z times the standard error. Master those three lines and averages will never mystify you again.